This is the next video in the series of videos that describes how to compose units. And in this video, we're really not spending a lot of time on how to compose units. We're really talking about the different kinds of models and spend a lot of time talking about those models. There's just one other type of model that I want to talk about before I finish this series, and that's a jammer model. So the scenarios that we have that go along with the tutorial scenarios, they don't really use a jammer model. A jammer model doesn't have any effect on the outcome of the scenario, but we want to put a jammer model in, again, because the purpose of these videos and the purpose of these tutorial models is to teach people how to build different kinds of models that you can build with Flames and to show how the models interact with each other. So modeling electronic warfare, and particularly jamming, is pretty complicated. It can be very complicated, and it's one of the more complicated things that you need to do, that you can do in Flames with modeling. So when we get to the videos on how to build the jammer models, there's going to be some information that needs to be communicated there, but we just want to show you here how they work. A jammer model is really just some kind of emitter that emits energy that can be received by other devices, and that somehow influences the processing of the reception of energy in those other devices. So a very typical example, and that's what we're saying is jammer, is we have some kind of device that's broadcasting energy in a certain frequency and certain amount of power, and there's other devices out there that are listening to in that same frequency, and this energy is picked up by the devices along with the energy the device is expecting, and that energy ends up disrupting the reception of the data, and now the receiving device is not able to discern the information that's supposed to be transmitted through the electronic signals, electromagnetic signals, and it ends up disrupting things. So there's a lot of different kinds of jamming devices that could be used. This one is kind of loosely intended to represent a radar, and the jammer models that we have in the static, the starter models, those jammer, there's only just one in there. Also, that's also intended to be a radar jammer, and you can set it up at different frequency bands and different powers and that kind of stuff. We take the power that comes from the jammer and we feed it into the radar range equation. So our radar models are at the radar range equation level. So if you're a modeler or a radar person, you know what I'm talking about when I say that. There are terms in the radar range equation where you're computing noise, and that noise in this case gets determined in part by the jammers, and so you have to have a certain a certain signal strength that you have to be able to receive before the signal gets through, and so all goes into it. But here our jammer model is a very simple subset of that, and all we're trying to do is illustrate the interfaces between jammers and sensors and antennas, because you have an antenna on the sensor and normally you have an antenna on the jammer normally. I'm going to create another unit out here, and I'm going to create them from scratch. I'm going to call them jammer. And so it's going to be a copy of my blue shooter. Then I'm going to go to the script here, and I'm going to leave the same platform model and the same driver, but I'm going to take off everything else. Let me leave that. Yeah, I'm just going to take everything off. And I'm going to employ a jammer. So employ jammer, and I'm going to go browse for that, and I've got one jammer meta object, and I'll put the start statement back in. I hit accept, and let's go take a look at my composition. You can see I've got a platform and a cognition model, so I can still position that guy, and I've got a jammer. Let's go look at the jammer. Jammer in this case doesn't have an antenna. Normally, jammers would have an antenna if it's a jammer that's going to be jamming other devices that also have antennas, but we simplified it just to keep it more simple. and it has a range, so that's also not realistic. You usually just have power, and how the receiver gets affected is determined by more complicated equations. We just put a max range in here, and we put a height so we can get the jammer off the ground instead of having it being co-located with the unit. So those are the only input parameters that we have for this jammer model. So let's go back to the unit now. So we have the jammer here, and we're going to go ahead and switch the commands, and we will locate this jammer model someplace. So I'm going to put a locate command, and I'll specify its location, and we'll put it over here and hit accept. And then I need to move this locate statement above the start statement. So there's my jammer right there. So what we're going to do in order to see the effects of jamming is we are going to use a tool that is supplied with the Flames Enhanced Analysis option. And it's called the Sensor Coverage Analysis tool. So normally, if you weren't using that tool, the only way you'd really know if the jammer was working is if you ran the scenario and a unit that you could detect one time, we turn the jammer on, all of a sudden you can't detect it. But that's not something that you can see real easily from the graphical interface. The sensor coverage tool lets us see the effects of jamming. So I'm going to pull that up right now. I'm going to go to Tools, and I'm going to go to Sensor Coverage. And again, you only get this if you have the Enhanced Analysis option. But if you're using the trial version of the Flames engine, it will include a trial license to the Enhanced Analysis option. So, and that's what I'm using for this tutorial. So I can run this tool. So this tool, I'm going to dock him now in this window. And I'm going to create a data set, even though I'm not going to save it. And I'm going to, I have to specify a platform that I'm trying to detect. So I'm going to specify this red truck. So the way this tool works is well, let me specify the input data, and then I'll come back and show you how it works. So I specify what I'm trying to detect, and I specify its altitude. And then I go down here and I put a list of the sensors that I want to include in my analysis. So I'm going to go here and I'm going to hit add, and I'm going to pick the blue commander. And that's all. That's the only one that I'm going to use right now. So that's the guy right here. And I'm going to turn on, I'm going to leave it set to radial, and I'm just going to leave these parameters just like they are, and I'm going to hit accept. And then I'm going to say compute coverage. So this is showing me what this sensor could detect. So because I don't have terrain masking turned on for this particular sensor, it's able to see in all directions. And I built the sensor to be an omnidirectional sensor, so it doesn't have a limit, field of view limit. So it's limited only by range. So if I turned on terrain masking, and you can go ahead and do that yourself, we did that in an earlier video. We modified the sensor meta object and turned on terrain masking. You'd see that certain parts of this fan here would not be drawn because it would be masked by the terrain. So I'm going to go make this a little bit. In fact, I'm going to change to, let me just make it down to like 2 degrees and compute coverage. And so now I've got a little bit finer drawing here. So before I turn on jamming, let me just give you a little bit more explanation about what's happening here. I've picked a particular platform. So it's a red truck, and I need a real platform with real signature attached to it to be able to perform calculations. And what I'm doing is at the altitude that I specified, I'm placing that truck all over the place. And I'm running my sensor detection algorithms to determine whether I could calculate whether I could see the truck if it was positioned at that place. And if I could see it, I draw a little short line segment. And then I go to another place and I check it there, and I'll draw another little line segment. Those line segments are 100 meters apart. So I draw a line out here every 2 degrees, and I step down that line every 100 meters. So these little line segments will be drawn. They'll be 100 meters long. And if I am able to see something, I'll draw a little segment. So I'm placing this guy all over the place along all these radials to determine whether I can see, if I could see a platform that was placed at that location. So I said I wasn't going to do terrain masking, but I lied. I'm going to do it because it's just more interesting to see this. So I'm going to go here to sensors, and I'm going to go to this commander sensor. And I'm going to create a new data set so I can make my own copy of this guy. So now I own this guy, and I'm going to turn on terrain masking and hit accept. And then I'm going to go recompute the coverage of this guy. So now you can see it's very different. He's up on top of this hill, but there's another hill over on this side, so the terrain's masking in this direction. And then you can see it kind of follows the terrain. So you can see it very different. It's important to note that this particular tool, little sideline, when it determines whether it can see that target, it's actually running the full sensor detection algorithm. It's not just a line of sight test. It's actually saying this particular sensor right here, actually trying to detect that particular target. So all the functionality of that sensor applied to that particular target is being used here. So it's a full detection calculation. So I'm going to go back and turn this terrain masking off, and then I'll recompute the coverage again. I get this perfect view of everything. And now I'm going to turn on my jamming. So whenever I turn on jamming, I don't have a way in this particular tool of selecting which jammers I want to use. It turns on all the jammers in the scenario. And so then I recompute coverage again. And you can see here that when I'm looking in this direction, because I have an emitter out here that's sending energy to me, I can't see targets that are over here, because this jammer is sending energy that is distorting my energy that I get from the target. So I can't see targets. And that's what jammers do. They prevent me from being able to see things. So if this was a self-protection jammer, and I'm flying around here, I'm moving around, this guy would not be able to see me. He wouldn't be able to shoot me. And because I'm using all of my engagement logic, it's using actual detection data. If I jam that guy, I just automatically can't shoot him. I don't have to do some statistical thing that says, oh, my probability of kill is lower if I have jamming on. I'm doing the math that says I can't see the guy, so I can't shoot him. Now, the reason that there's such a narrow little slice here is because of something that I mentioned when I was talking about sensors. Our sensor for our this blue sensor that we have attached to this guy right here, he's got an antenna. And we looked at that. He's got a real narrow main beam. So we're only jamming in the main beam in the way this particular thing. That's not how it always works. That's not how it works in the real world. You can get the back lobe and side lobe energy coming in, but we're not doing any of that. This is a very simple model. We're only allowing the jammer to influence things in the main beam. So if this jammer is in our main beam, then we're considering the energy that comes in here. And in our case, if I get any amount of energy at all coming from a jammer in this particular sensor, I'm saying, okay, I can't see anything. So I get a very, very rudimentary, unrealistic equation that I'm doing. But just to illustrate this, let me create a new data set. I'll accept this guy. So now I've got my own copy of this guy. Let me make his main beam wider. Hit accept, and then I'll go back to my sensor coverage and recompute coverage. So now I've got this wider area that where I can't see. So again, in a real scenario, you wouldn't be able to see this graphics. You wouldn't really know what's going on. All that would happen is that you'd have a set of units that can't be detected, and hence they're not being engaged. So, and you can make the calculations that are being performed by this jammer a lot more sophisticated than what we have. But as I've explained multiple times, the purpose of this jammer model is not to teach you how to do the math for jammers. It's to teach you how to implement a jammer model and have it properly interacting with all the other models. So what's the function of the model? How does it affect calculations? Not performing the calculations, but where you would get that data and how data gets passed back and forth between sensors and jammers and targets. All that's illustrated by this very simple jammer model. So this is an advanced topic. If you don't care about jammers, you can ignore what you've learned here. But I wanted to give you this because I want, in these tutorial models, we're giving you an overview of each of the main classes of models that you can implement in Flames. So thank you for watching, and thank you for using Flames.